So in this video we're going to determine how you receive digital signals, bits. How do you recover from that analog signal that's sent through our analog channel? How do you recover those bits, and how do you do it well? In particular, I want to focus on this word optimal. We're not going to prove it here, but the receiver I'm going to show you here has been proven to be optimal. There is no better receiver in the sense that the error probability of making an incorrect choice for the bit is the smallest it can be for the receiver I'm going to show you. And that's going to lead us to be able to compare the performance for different signal set choices. Turns out it's an interesting contrast to the bandwidth calculation we did in the previous video. So here is to recall the digital communication model, both for analog and digital. And I want to point out that the channel is exactly the same as the one we've been talking about. What's more important here in the digital case is the presence of this delay. That turns out causes all kinds of problems. In addition to the attenuation and the noise, again we're going to assume that the interference is very small. The delay is important because now we have to figure out where those bit interval boundaries are. We don't know that delay, which we usually don't. Somehow the receiver and transmitter must be synchronized. And we assume that there's no other information available to the receiver other than what it receives. It's going to receive a noisy signal that you don't know the delay tau. So the synchronization problem is to find those bit boundaries accurately. I'm going to assume here we found those bit boundaries somehow. To keep it simple, it's actually pretty complicated to build a synchronizer for bit streams. So we're going to assume these are the actual bit boundaries. You can see them labeled by the dashed lines. And somewhere buried inside this very noisy signal is a baseband BPSK signal set representing a particular bit sequence. What receiver will tell us what that bit sequence is? I think you'll all agree that looking at that signal as it is and by eye trying to figure out what the bit sequence is pretty difficult. It's going to turn out, as I show you in the simulation I'm going to run, it's actually very easy in this case for the optimal receiver. It's astonishingly easy. Let's see what that receiver is. It's called the correlation receiver because the multiplication of one signal by another and integrating is called correlation, just the name. And here's the way it works. So we're assuming that we're looking at the signal over one of the bit intervals, and it's called bit interval n. So I'm going to take that signal, the received signal coming out of the channel, I'm going to multiply it first by the signal representing bit 0, and then also by the signal representing a bit 1, integrate, and get an answer for each. So that's mathematically is what I do. I take the received signal, no matter what it is, and I multiply by each of the two signals. I then want to compare them. Whichever one was the largest is my choice for the bit. Okay? So I write that mathematically as being the argmax. This may be a new mathematical notation. If you get the arg for a second, max means, of course, find the maximum with respect to the signal index. We don't really care about what the value of the maximum is. That's what maximum returns. It returns the maximum value. What we care about is which value of I has the maximum, and that's what argmax means. Which index has the largest value? I don't care what the maximum value is. I just care which one is biggest, and that is going to be our guess, our best guess. It turns out our optimal guess for what the bit was. And this is a very simple operation. You multiply by a signal, integrate, and pick out which one is bigger. So let me show you how this works, at least in this situation where there's no noise. So let's assume we have our BPSK baseband signal set. And what I'm going to do is I'm going to send a 0 through this and try to see and show you that this works perfectly in the case of no noise. So during the time interval that we're talking about here, R of t is the same as S0. So we get S0 squared, which is just has a value of a squared. Integrate that over a bit interval, we get a squared t. In the other part of the receiver, we multiply by S1. Well, that's given by minus a times the plus a, because S0 is what we're assuming was sent. That's what RT equals. We get a minus a squared integrated over the interval. We get minus a squared t. Now, what happens is we choose the biggest of these. Well, it turns out for BPSK, one is always going to be the negative of the other. So which one is positive is the guy that we want. And so we would choose that. And of course, that turns out to be absolutely the right case. And it's always going to be that way in the case of no noise. So we have a perfect receiver that creates no errors on its own when there's no noise around. The channel is being nice to us. Well, now suppose things are a bit tougher. There's not only noise, but there's attenuation. All right, so exactly the same scenario. I'm sending a bit of 0, so R of t is S0 times alpha plus noise. So the signal term, you might call it that, for each of these is clearly going to be this, and the values are now attenuated by alpha. Well, that has the effect of bringing them closer together. Instead of the value being plus 1 and minus 1, they could be plus a tenth and minus a tenth. They're much, much closer together in value. If alpha, for example, is a tenth. So right away you see it brings them together closer. What happens with the noise term is that these are random numbers. The bigger the channel noise is, the more random they're going to be, which means you could confuse them. That means this value could be bigger than the correct one, and an error will occur. So it's because of the noise that creates errors. And so there is a non-zero probability that the bit choice is wrong when we have noise, and the attenuation doesn't help one bit. It makes it worse. So how do we figure out that probability? We're going to figure that out in a second. I want to show you just how good this receiver is before we get too far along. So I'm revealing for you what the bit sequence was, 101001, and it's carefully labeled here. And I show in dashed lines what the transmitted waveform looks like. What I'm about to do is plot each of these outputs here. I'm going to use a red one for the 0 part of this, and a blue for the 1 part of this. And what I'm going to plot is this quantity instead of what's indicated here. And so the value, only thing that matters is the value of that interval at each of these bit boundaries. Okay. So that's where we're going to look to see which one is largest, but it's interesting to see what it looks like in between, as you're going to see in a second. So you send our very noisy signal through our correlation receiver, and the first thing that strikes you is amazingly clean. The noise has been greatly reduced. It's just astounding. And again, the blue signal here corresponds to the 1. The red signal corresponds to the 0. And you can see that when the bit was a 1, it's very clear the S1 part of the receiver goes up dramatically. S0 signal has to be the negative of it, and it's clear that we made the right choice there. 1 is bigger than 0. Now the bit in the transmitted bit sequence flips, becomes a 0, and sure enough, the outputs our receiver flip, and a 0 becomes the biggest. And it's, in this example, It's always correct. Just amazing to me that for something this noisy, the correlation receiver got it exactly right every time. This is not going to happen in general. Even for this signal to noise ratio in this example, eventually there's going to be a time in which the correlation receiver picks the wrong bit. A 0 will be sent, and it's going to say, no, a 1 was sent, and it's going to be wrong. There's no way of correcting that because we're assuming the only link between the transmitter and receiver is our noisy channel. Well, like I said, what is this probability? Well, it turns out it's a complicated analysis and is clearly affected by signal set choice through a relationship which has to do with the energy of the difference signal. So what's important about the signal set is the value of this interval, which is, we now know that when you square something and integrate, that's energy. And this is the difference between the two entities in the signal set. So whatever, the bigger that energy is, it turns out the smaller the probability of error. That's a pretty important factor here. And we're going to see how the difference between BPSK and FSK in just a second. Also, the channel attenuation enters into it. And as I indicated, the greater the attenuation, the smaller the signal is coming through the channel. That's going to make the probability of error go up. And also, of course, is going to depend on how variable the noise is. The more variable the noise, probability of error goes up. And a subtle aspect is it depends on the probability distribution of the noise. So we have to assume about something about the range of values and which values occur more frequently than others in the noise. And what we're going to assume is the so-called Gaussian model, where the noise amplitude tends to have this kind of distribution. So this says that the amplitudes close to 0 occur more frequently, and very infrequently do you get very big values. So this plot here basically reflects the probability of getting at a given amplitude at any particular time. And this Gaussian, which is given by something that looks like e to the minus x squared over 2, turns out to be a very common noise model that's used all the times in communication. Well, let's see what the final result is. I'm not going to derive it here. This result you can derive in any digital communication course that you might find. It's a well-known result. And the final answer is that the probability of error is given by a function q that I'll show you in a second. The argument of q is the important thing. So here's that signal difference energy. Here's how alpha, the attenuation, enters into it, and n naught comes in the denominator. So what is q? Q turns out to be what's known as the tail integral of that Gaussian curve. So if I were to plot that Gaussian again, here it is. The q function, notice, is an integral from x to infinity. So start here at x and you get that area. So clearly, as x gets bigger, q gets smaller. So it's a decreasing function, and I plot it here on logarithmic coordinates. This is really interesting how quickly the q function goes to 0. So notice that if q of 4, that turns out to be a value that's just about 3 times 10 to the minus 5, a very small number. Well, we want probabilities of error that are small, and it turns out this reflects how well the correlation receiver works. But let's look at this in more detail. The bigger the argument for Q, the smaller PE is. We want a small PE. We want this to be as big as possible. The channel attenuation is not going to help. It's going to make it smaller. The noise, the the bigger the noise term, N0 is, that also makes it smaller. The only thing you can do is use more transmitter power, that's the capital A in the BPSK examples, and the signal set choice is that even for a given transmitter amplitude, you want this difference between the two signals in your signal set to have as big as energy as possible. So, nothing, like I keep saying, nothing good happens in a channel. It attenuates, it's noisy, that's going to hurt. The probability of error is going to make the probability of error bigger. Only thing you can do is try to compensate for it by signal set choice, that's a design choice, and how much transmitter power you have. So let's see the signal set, the effective signal set. So I've normalized things in terms of what's called EB, which is the energy per bit, which each of them puts out the same amount of energy for a given bit, whether it's a BPSK or FSK, I'm assuming modulated here. Notice that in here there's a factor of 2. Well, that factor of 2 is entirely because of the BPSK. FSK does not have that factor of 2 that pops up. Well, that makes this argument always bigger than it is than for FSK. And you say, well, what's a factor of 2? How important can that be? Well, it's because of the nonlinearity of Q that it can have a dramatic effect on the probability of error. When the signal to noise ratio is 10 dB, I want you to note that there's about 2.5 orders of magnitude difference. The probability of error is 2.5 orders of magnitude smaller for BPSK than FSK. So it turns out BPSK can be far superior to FSK. If you go to lower signal to noise ratio, there's not much difference, but the probability of error is only about 1/10, which is probably unacceptable in most applications. Now, I'd also point out that it's been proven that BPSK is the best possible signal set you can have. There is no other signal set for a given EB that produces a smaller probability of error. So BPSK is optimum, but as we've shown, FSK can use a smaller bandwidth. So here you have a classic trade-off. Do you want small PE? Well, that might mean you need a wider bandwidth channel, and FSK takes a smaller bandwidth, but your performance isn't as good, and it of course depends on the signal to noise ratio that you get, which is EB over N naught. All right, so let's summarize now. Digital communication systems are not inherently perfect. The noisy channel, and the channel attenuation for that matter, introduces bit errors that occur with some probability, which we want to make as small as possible. You don't have much control over the noise or the channel attenuation. That's not what you can control as a designer. You can, to some degree, control the transmitter power. You have to use what's available, but you can certainly control the signal set design. That's up to you. And that can have a significant impact on performance, although it doesn't look like it from the formulas. Now, I would point out that the worst probability of error occurs, you get it's a half. It turns out the probability of error should never be worse than a half, which I guess is reassuring. But how small should PE be? So let's think about this. Suppose you have a data rate of R bits per second, and let's assume for simplicity that the probability of error is 1 over that rate. So in my example, if we have a 1 megabit per second data rate, suppose PE is 10 to the minus 6th. That seems like a pretty small PE, but I point out that means you get 1 error every second on the average, and that's probably unacceptable. I would think I would want something at least like 10 to the minus 9, but even that means an error on the average every 1,000 seconds, which again may be a bit more frequent than you can willing to put up with. So this may seem like we're kind of stuck. The only thing we can really do to overcome this is have more transmitter power so we can boost the signal to noise ratio to make PE smaller and smaller. Well, that turns out not quite to be the whole story. Just after World War II, an engineer named Claude Shannon developed information theory, which we're about to talk about. He showed that it is possible in digital communication to send bit sequences through analog channels that introduce noise. You can get that bit sequence through with no error at all. Zero. You can overcome the noise that the channel introduces. That's what makes digital communication a lot of fun, and I hope you join me for the succeeding videos to hear that story.